This is a short introduction to the basic functionalities of SCINE Heron, the graphical user interface to the SCINE software package. This demonstration accompanies a more detailed paper linked in the description below. Heron, as well as all other SCINE modules shown in this video, are freely available and open source. In the following, we will go through the individual modules and demonstrate how Heron facilitates the exploration of chemical reaction spaces. The Eschenmoser-Claisen rearrangement will serve as an example throughout this video. Let's assume that we have a specific molecule whose reactivity we want to explore. We can either create its structure directly in the software or load its Cartesian coordinates from a file. What we see now is the molecule, as well as the most important settings on the right and the electronic energy graph below. We may select a semi-empirical method and start the electronic structure calculations in the background. From now on, the SCINE module Sparrow runs continuously semi-empirical electronic structure calculations in the background. As you can see, the structure then always relaxes towards an energy minimum. We can either interact with the molecular structure using the computer mouse or, as we are doing here, using a haptic force feedback device. The haptic device generates a force from the calculated negative semi-empirical gradient of the energy against the direction of motion of the selected atom, and therefore allows one to literally feel the quantum mechanical force acting on this atom. If we now want to perform a specific reaction, for example the methanol extraction, we can do this specific manipulation of the molecular structure and feel the activation barrier simultaneously. Once the transition state is crossed, the structure slowly relaxes towards the product. When the reaction is complete, the trajectory can be viewed, edited, and exported. Furthermore, a reaction template can be extracted, which can later be exploited to accelerate automated reaction explorations. If we are now interested in how good our guess for the reaction trajectory is, we can check whether the SCINE module Readuct finds it automatically. In the Readuct tab, we can add the product structure as well as the reactant from the start directly from the molecular viewer. Now we can first optimize the starting and end structures. As you can see, the number of iterations was not sufficient for our manually created product structure to converge. We increased the number of iterations, which is now sufficient for the product to converge as well, indicated by the green box. Now we can carry out a double-ended transition state search with our B-spline-based algorithm. This results in an optimized reaction trajectory, of which we extract a transition state guess that we can optimize further. So, what if we are not only interested in this specific reaction, but want to know what other reactions our reactant may undergo? Or in other words, what reaction network may be created starting from this reactant? First, we connect to the database, which allows us to access the other tabs related to Chematon. In the Chematon tab, we can define the electronic structure settings as well as a series of Chematon-specific options. Now we are selecting the method as well as solvation model and solvent. For example, we can calculate a Hessian on all structures to explore the reaction space with enthalpies and free energies. Here you can see and adapt all settings related to this task. We may consider another example. Say you might be interested in all possible conformers. Again, you can define additional settings. If you want to start all engines simultaneously, press the play button. This results in many calculations. Feasible here, but in general one would limit the number of calculations by adding more filters. Now we can see how our database changes in real time. But what does this reaction network look like? In the Reaction Network tab, we can open the current network. We can now explore different compounds, dots, and elementary steps, double arrows. We can traverse the reaction networks, switching from compound to compound, listing all reactions for a given compound. However, what if we have many elementary steps and want to know the best way through the network from starting compound to product compound? Manually, this quickly becomes unfeasible. For example, the Eschen-Maser-Claisen rearrangement consists of 4 elementary steps. The Pathfinder module is precisely designed for this purpose. All we need is the starting and product structures. The starting structure is trivial, as this is the initial compound we looked at. However, to find the product, we need to dig deeper into the network, which requires us to filter out irrelevant compounds. We leverage a substructure search to find all compounds containing a chain of 5 carbon nuclei and an amide group. We build the corresponding substructure in our interactive molecule editor after deleting the previous structure. Displaying all compounds with that substructure shows that the reaction network is still too large to find the wanted reaction product. Hence, we additionally impose a limit on the various nuclei present in the compound to exclude those that include additional functional groups. Now we can gather all the necessary compound IDs to find the various reaction paths in the network. The reactions and compounds of each reaction path can be viewed directly within the path, and the energy diagram can be constructed for the given path. If you are interested in Heron in more detail, please consider the paper linked in the description below. If you are interested in the SCINE modules, we provide a link to a second paper which focuses on the whole SCINE package.